This
And
conference will now be recorded.
welcome everyone. Happy New Year. We have today a presentation by Dr. Helmut Feder. As usual, we go with a short bio. Helmut studied theoretical physics in Braunschweig, Germany, and Uppsala, Sweden. He did his PhD in experimental physics in Enschede, Netherlands. He did 8 years of postdoc working on quantum physics with single defects in diamond with Professor Wrachtrup Group in Stuttgart, Germany. In 2016, he founded the company Swabian Instruments together with colleague Michael Schlagmüller and Markus Wick. Since then, Helmut has been running the company as its CEO. So I met Helmut this year 2 3 times, I think. Yeah, one time I met them in ISPCS, and then we had another one in ITSF. And it's very interesting. In ITSF, I brought a prototype for this PTM, and then Helmut came over, and then he basically put one of the instruments there, started basically testing the difference between the PTM TGPIO output and the PPS output of the NIC. And I was really impressed how easy everything was. Like, for example, there was a problem time to time. You get like this because the CPU sends a toggle rather than like an assignment. And sometimes you had like this like a 180-degree shift. And there was literally just one button, and then the whole thing was getting like reversed and like basically rising edge or falling edge. And then the software is pretty cool. Like you can run it on Mac and Windows and on Linux. And then I was like very interested in how this whole thing really works, what's basically under the hood. So I asked Helmut, and he agreed to basically give us a presentation of what really goes under the hood. So with no further ado, Helmut, the floor is yours.
Thank you very much, Ahmad, for this very, very kind introduction. And yes, indeed, it was absolutely a pleasure for myself and my team also to enter this very exciting community that's working on time and frequency stuff in a very relevant and applied domain, I guess, in the world's economy and our society. So it's really a huge pleasure to be here and talk about what we've been doing over the past years. So I've called this presentation Time and Frequency Measurements with Picosecond Streaming Time to Digital Converters. So certainly our technology, or I hope I can show you that our technology is maybe quite a bit broader than what is covered by this title. Nevertheless, this is really what has kept us busy and what has caught most of our excitement over the past years. All right. So I would like to give a brief introduction about us, like the team and our company, and then we'll later go into technical details. And I've brought a lot of slides and a lot of stuff that I can talk about. But I should stop at some point. So maybe first to get a rough idea, Ahmad, so how long should I talk about ideally? What's the most ideal time?
You can talk all the hour, and we can extend it since I mean, if people have to leave, they usually leave. The whole thing is recorded. They can come back later, so no limits.
Excellent. Okay, perfect. Thank you very much. All right, so just very briefly, so as Ahmad mentioned, I did 8 years of postdoc in quantum physics in Stuttgart, and I was working on these NV Sanderson diamond, and these are single defects in the diamond crystal that have a spin 1 ground state. These are beautiful quantum bits with very, very long coherence time, and you can use them. So if you compare it to the superconducting quantum stuff that's done by Google, IBM, and so on, where coherence times are maybe on the 200 microsecond range or so, with NV Sanderson diamond, you reach coherence time of up to seconds at room temperature, right? So no cryostat. At room temperature, you reach 1 second coherence time. So beautiful quantum bits. They have their own challenges, especially in terms of scaling up, because these are individual molecules in the crystal. And engineering ensembles of molecules that are coupled in specific ways is certainly a challenge. Nevertheless, highly interesting quantum systems. And to study them, you use basically a laser scanning microscope. So you shoot green light on a single molecule and you detect the redshifted fluorescent photons. And you can imagine single molecules, these are really very faint objects, and when you work with them, you really want to detect every single photon. And to do then quantum algorithms and so on, you have a lot more signals and electrical triggers. And I basically wanted to have a technology that allowed me to process these single photon events and other triggers in a generic and agile way. And so I put up a job posting at the Uni Stuttgart looking for a talented electrical engineer that can help us implement time taggers and time event processing in FPGAs and C++. And after 2 weeks or so, I had 20 applicants, and I assessed them all very, very carefully. And among them, there was one who stood out, and that is Markus Wick, who you see on the right-hand side, who now, about 10 years later, is our CTO. And he basically developed the first FPGA core of the time tagger back at the time. After 3 months or so, he had the first instrument, which became a big success in my research group. And then later in the wider physics faculty in Stuttgart, and then sort of spread around the globe in the quantum optics research community. All right, and also in Stuttgart, I met Michael. He's really this type of very, very careful electrical engineer who has this, let's say, this eye for the detail and is this has the skill to develop PCB boards in one shot, not much revision, and he naturally became the one in our team who takes care about our operations, production, quality, and customer success. Me as the CEO, I'm mainly responsible for strategy and business development. All right. So what do we do? So we really do streaming time to digital converters. And here you see our product series. That's the time tagger series, as we call it. And these are FPGA-based time to digital converters. With a resolution down to 1.5 picosecond, RMS jitter by now, up to 18 input channels, dead time down to 1.5 nanoseconds, a data rate up to 70 million tags per second from the hardware to the computer. In the field of single photon detection, these type of hardware specs are really outstanding hardware specs, and I guess by today we have really, bypassed all technology on the market or have become technology leader in terms of TDC specs. However, really the reason why we established the company and really the main thing that I guess makes a difference is not so much the hardware specs, it's really the architecture behind it. And since you guys all have a strong technical background, I'm really happy to share it today. Okay, so really on the left-hand side, this picture, this is taken from Tilman Fau's lab at the Uni Stuttgart. So that's a quantum optics experiment. And you have this table full of mirrors and so on. So I guess pretty much similar to stuff that has been shown in previous talks here in the OCP tab by people from NIST that have talked about atomic clocks and so on. So this type of experiments. And so we care about the digital signals coming out of this. So obviously there's a lot of analog detection involved as well. This is, let's say, not our business. We worry about whatever digital signals come out of that. And what is maybe specific for physics experiments, not necessarily a requirement for the way we record signals, but what's typical is that you have digital signals that do not have so high data rates. So it's not like 10 gigabits of events coming out of that. The data rates are often not so high. However, you want to record signals with very high precision. Okay, and in this case, the time taggers are sort of a very useful approach, though in principle they can also be used for higher data rates. In any case, so think about a set of digital signals. And in a way, if you know that the timing or the precise time of any rising edge and every falling edge in this signal, you sort of have described the set of signals completely. So in a way, so from an information perspective, there's just not more information inside these signals. From a mathematical perspective, these are like piecewise constant functions, right? So it's just 100% information captured if you know the time is when a rising and falling edge toggle occurred. So now we abstract this. So a set of digital signals can be represented, or we represent a set of digital signals as a stream of timestamps. At what time there was a rising event or a falling event on which input channel. Okay, so now this, and this is what we call a time tagger. So now this, in principle, is not totally new, or certainly is not new. So many others have done that before, and you could think of some of the big particle accelerators that are running around the globe as gigantic time taggers, where time events are generated. However, in most cases, you will get these timestamps written into a file. So that's maybe some text file that contains these timestamps. Maybe it's a binary file, sometimes in a weird type of format. And then the work really starts. As a PhD student, you start writing MATLAB, or these days, probably more likely Python scripts, or any other programming language, to go about and process this data and extract from these timestamps the quantities that you actually want to measure. So in a way, what we've done is implemented a time tag stream processing engine, you may call it like that, that allows you to hook any type of processing threads that all run in parallel and on the fly onto this time tag stream. And that makes it very easy to use. And so to give you one example, so you may be interested in just the average event rate on whatever. So in channel 1, you have hooked up a single photon detector, and you just want to know the average count rate on that detector. So then this processing thread, just you specify a bin width, and that processing thread will evaluate the number of photons in each bin, and it gives you this type of time trace counter plot that you see on the lower right-hand side. Or one thing that we used to do with NV Sanderson Diamond is laser scanning microscopy. So now you have your microscope with a piezo scanner that drives a laser or moves a microscope objective, either way. And whenever that thing moves by pixel, it generates a pixel trigger. So now you hook up the pixel trigger to channel 3 of your time tagger, and the time events when the pixel trigger was fired will appear on the software side in the time tag stream. And then to generate an image, you basically calculate or integrate the number of photons, or count the number of photons until the next pixel trigger comes, and that's then the intensity in that pixel. And this way you can generate laser scanning microscopy images. Or you have start and stop events like is shown on the top. So in this case, it's a molecule at which you shoot a laser, and the fluorescence photon comes out sometime later, and you're interested in the, let's say, average time when the fluorescence photon comes out after your laser shot. And what you do in this case is you measure the timestamp of the laser trigger and the timestamp of the photon detector, and you do this in a repeated way and put that in a histogram, and out comes such an exponential decay curve, which is the fluorescence lifetime. Okay, and there are numerous applications in single photon detection. So this is what we've traditionally been doing. But then more recently, and that the whole thing started, I guess, back in 2018, when somebody from Telenor contacted us and asked us, hey, I would like to measure, so I have these 1 PPS signals, and I would like to measure the time difference between these 1 PPS pulses and understand what's their statistics and so on. And back at the time, my initial thought was, okay, sounds interesting. Could you tell me what is a 1 PPS pulse? So we really learned about this and started to get into that field. All right. And one thing that it's also possible is now if you have periodic signals, like a 10 megahertz clock signal or so, you can generate the 10 million time tags per second on one 10 megahertz clock channel and 10 million time tags on another channel from another clock, and then on the fly calculate stuff like LR deviation, MDEF, TDEF, and so on, frequency, phase, as you see on the top left side. And I will talk about that in a bit more detail in a second. And another application is a logic level oscilloscope, which you can sort of extract directly from the time tag architecture, which I will also talk about in a second. All right. So that's already the sort of the take-home message. So I hope I will show you in the following of the talk that a multi-channel time-to-digital converter plus, so combined with, let's call it a well-written time-tag stream processing engine, is really a very powerful tool for digital measurements. All right. Just before I go into the technical details, just a little bit about our company so that you get, would like to give you a bit of an understanding about how large we are, what we do in terms of business. So we sort of build business around this technology. And one important part is single photon counting, which is where we come from. So that's time-resolved microscopy, cold atoms and ions, time-resolved fluorescence, fluorescence lifetime imaging, LiDAR, time of flight measurement with light, and so on. And then, as I mentioned, the time and frequency recently has really become a very relevant part for us, which is clock oscillator testing, so frequency stability analysis and synchronization testing, which would be the comparison of 1 PPS signals. Another part is dynamic light scattering, which is also an application of single photon counting, where you detect particle size. For example, in the COVID-19 vaccine, you would measure the size of these mRNA particles by dynamic light scattering, which is a statistical method where you basically measure an autocorrelation of single photon events. I will skip this part today. All right, then, who are our customers? So it's really on the single photon side. It's a lot of universities around the globe, also NASA and NIST, and also manufacturers of single photon detectors such as laser components and accelerators. And then in time and frequency, we're very proud that Cytam has started using our time takers to actually characterize their silicon MEMS oscillators relative to an atomic clock. Telenor mentioned they're really doing 1 PPS comparison, and Ahmad mentioned that he started using time taker to characterize the 1 PPS pulses of the Intel NUCs. And also the German National Lab, which is the PTB, is today using time takers to basically measure the atomic clocks that are run in Germany to disseminate the time. And also Deutsche Börse has recently acquired a time taker to measure 1 PPS pulses of network switches and characterize the white rabbit links. All right, just to give you a brief idea, so we started out in 2016 as a company with 3 people, and by today, this year, we are around about 30 people, and we've recently established an office in the US in Boston, and just last month we established an office in Shanghai. Okay, I will skip that part otherwise. So why do people typically use our system? So it's really the flexibility. So because of the software-defined approach, you can really implement a lot of different applications in a very flexible manner on the software level. There is a huge library of processing threads, which makes it typically very easy to implement stuff. So typically it's just a few lines of code to implement complex digital measurements on the software level. And also our instruments have quite a large number of input channels, which makes them very scalable. All right, just a quick idea to give you an idea of who we are. So we are about 30 people, and 2/3 of these are electrical engineers. Then 1/3 are scientists, so physicists, typically with a PhD, And then we have a bunch of people in business development, operations, and also students. Those are mainly electrical engineers that, some of them do really very leading edge electrical engineering work. All right. That's basically our vision. So on the one hand, it's about developing, our goal is really to develop game-changing scientific instrumentation, generally in the domain of digital signal, digital measurements, or digital signal generation. And also, that's maybe more the founder's perspective. We would like to give all these bright minds that we have in the team the freedom to create extraordinary technology. All right. So that's it about the quick company introduction. So it's really, so our goal is really to revolutionize digital measurements, enable our users worldwide to implement their ideas faster and more efficiently. And with that, I would like to come to a brief overview of let's say real content of the presentation for today. First, I would like to talk about FPGA-based time-to-digital converters, so to really explain a little bit how we implement the TDC in the FPGA. Then I would like to talk about our architecture, so really what is behind this time-text streaming idea and how do the different bits and pieces come together. Then explain a bit how we use that to do time and frequency measurements. And I guess the three last parts are sort of optional. So a few slides about photon number resolution, also work that we are doing towards a 500 gigahertz optical sampling scope. And then I have a few slides about the work that we do towards a TDC ASIC and 22 nanometer FDSOI. All right. So this is sort of the oldest TDC type, which is a start-stop, right? So there's a start trigger and a stop, and the stop could be a periodic clock. And the time difference between the start and stop is then converted into a pulse, integrated and read out with an analog to digital converter, right? So that's sort of the oldest type of TDC that has been used for back in the days. And today, most ASIC TDC architectures, and especially those in FPGAs, they are rather based on the TED delay line approach, which I briefly show here. So think about a chain of amplifiers or a chain of delay elements. Typically, these are just inverters, inverting amplifiers, or let's say for simplicity, non-inverting amplifiers. And next to them is a series of flip-flops. And the signal that you would like to measure, you inject into this inverter chain or amplifier chain, and then you latch the flip-flops on a common clock that is provided to them with a very well-balanced clock tree. And with that, you are able to generate sort of a snapshot of the propagation of the signal that you have injected into this inverter chain. So what you will get as a tap output is something like 11111110000, and from the transition between all the ones and the zeros, you know how far the signal has propagated. And on the right-hand side, you see how that can look in an FPGA. So there you really use the carry chain of the slices as the delay elements, which are the fastest elements in the FPGA, because they need to provide the carry during an addition. So these really are optimized towards low delay. So this is really a floor plan snapshot how it may look like. And here you see already one thing that can go horribly wrong, because you see here that though many of these delay lines have a big gap in the center, which would mean that there would really be one very, very large bin. So what you would like to have instead is a delay line that is really a continuous chain of these delay elements. And one thing that you really have to care about here is the clock domain crossing inside the FPGAs, and you have to make sure that the delay lines are limited to single clock domains. Okay, so that's the basic principle of a tap delay line TDC. And in the next slide, so apart from this thing that I've mentioned here, that the delay line really has to be continuous, in the next slide I would like to highlight some of the challenges that you would like to come across. Okay, before that, would like to point out that this is not new, so this FPGA-based TDCs have been made since somewhere, I think the earliest papers are even before 2000. FPGA-based TDCs have been made, and these are just few papers. There are certainly more, and it would be too much to highlight them all here. One is by Claudio Favi from EPFL in Lausanne from 2009, which is really a reference where he already back at that time made a 17 picosecond RMS TDC. There's a Polish team at the Military University of Technology in Warsaw, which also have made excellent TDCs, and also the team at Politecnico di Milano that really has done great work on and published a lot about time-to-digital converters in FPGAs. So if you want to read more, I recommend all of these publications.
I came across this method actually in a book from Stefan Hensler. I think you've seen it. It's like from Springer.
Yes.
It's like a very nice, comprehensive book. It goes through everything. I really enjoyed it.
True. Yes. Yes. He has. He's really. This is really a very important reference as well. Absolutely.
Yeah.
Yep. Thank you. All right. Just to explain a few of the challenges. So believe it or not, what happens sometimes, so you would guess that, okay, this pulse propagates through there, so you would get 1 1 1 1 1 0 0 0, but believe it or not, sometimes you get 1 1 1 1 1 0 1 0 0 0. And that can happen if simply if the clock tree is not that perfectly balanced, so that the flip-flop that is next in the line switches earlier than the other and the delay is so short, then you get this type of stuff, which is called bubbles. So you can think about it, if you think about this code like a thermometer, it's really like a bubble in the thermometer. So you somehow have to deal with those effects. And I will not go into details here, but just mention, okay, this is one of the challenges that you got to tackle. Another one is obviously temperature drift. So this in this sketch, the tau that is written next to every delay element that is ideally in principle constant, and the same for each delay element. In practice, if you really go down to this few picosecond level, it really starts to matter that with temperature, with voltage, also supply voltage or other things, the delay changes. And this is something that you have to compensate. So you really have to calibrate this delay elements very, very carefully. And we do that continuously on the fly. And one way how to do that is mentioned in one of the last papers that I've shown there by the Milano group. They have described in detail how calibration can be done. So calibrating the tap delay lines in FPGAs, this is one of the key things that requires a lot of thinking, a lot of work to get things right and to get down to really low levels. Another thing that is maybe not mentioned so often in the literature is crosstalk, and I would like to maybe spend a few slides about that to highlight that. So here's the experiment that you do, and that really comes from the single photon application domain, so from that application area. So imagine you have two single photon detectors and you hook them up to your time tagger, each detector on one independent channel, and you then open the window a little bit or open the sun blinds of your lab a little bit and you let in some faint sunlight. That is a very nice way to generate totally random events. So each single photon detector will click and generate output triggers at completely random times. And you put those to the time tagger, generate timestamps, and what you then do is you calculate the cross correlation of these events, which in practice means a multiple start, multiple stop histogram. So for every photon event on detector A, you look at, you take every photon event on detector B, get the time difference between each pair of events and put them into a histogram, and you collect all events that fit into a histogram of a certain range. So you don't need a huge histogram range there. And obviously, so what you expect is shot noise, right? So these are Poisson distributed counts. And in each bin, well, if you have at a mean of 1,000 events in each and every bin, then you expect to have 1,000 events in that bin, but you expect square root of 1,000 to square root of n variation. So really just Poisson distributed shot noise variation. As this, so I've plotted this. This is an artificial plot that I've generated on the right-hand side. So this is what you expect how it should look like. So a noisy shot noise limited signal. But this is what you get. So this was with one of the very early TimeTagger 20 FPGA cores that we had. So this is really historic data. By now, our data looks very different. Nevertheless, so this is what you then get after integrating for a long time. So here, in this case, in each bin, there are 17 million counts accumulated. And you see immediately, this is obviously not random noise. There is really structure in these signals. And this sort of, so you see here the green lines is what the standard, what the random noise would be if it was random noise, and the red line, this is the RMS of this sample. But actually, you don't need to calculate this. You see by eye that this is not random noise. This is really structure. And there are really two things in here. So you can separate this into two different effects. So one is what I have called marked with A here. These are spikes, big spikes that are close to zero, close to a time delay of 0. And this is crosstalk between channels. And there is another pretty nasty effect, which is maybe a little bit hard to see, but this noise that somehow looks like noise further away from 0, I've marked it as B. This is actually not noise, these are periodic spikes. So you really see these periodic events there. And this is coming from unequal bin sizes. I would like to discuss both briefly. So what is this crosstalk? How does that happen? So, I mean, it's a digital signal, so you detect events, right? So, and for sure, you have set your trigger level properly, so no events are lost. Okay, so this, for sure, this is right. But what happens is that events are shifted in a conditional way, shifted in time in a conditional way. So imagine at channel 1, you have a square pulse coming in, and of course, in real life, the rising and falling edges are never infinitely sharp, right? They have some finite slope, as I've sketched here. And you set your trigger level, and that determines the trigger point where you will detect the event. And now imagine at channel 2, a similar square pulse is coming in, and that came earlier. And simply imagine that, let's say 10% of that signal and in a completely analog way couples into the other channel. So simply a small percentage of that is added to the other channel, and that's what I've plotted on the left-hand side in the third row. That's simply the first signal plus some 10% of the second one, just added. And that simply changes, that's because of the finite slope, it changes the edge, and because of that moves the trigger point. So that means that the timestamp is shifted by a small amount, and a specific small amount, depending on whether the other event is there or not. So that's really a conditional change of the event. And this leads to these artifacts around 0. And you see that actually there are two spikes, the main spike at 0, and there's another one at -100 nanosecond. and another one at plus 100 nanosecond. And these are really the falling edges of the output pulse of the single photon detector in this case. These are much wider and not that high because the pulse length is not that well defined. Okay, so that's what analog crosstalk can do. So which you see in an extremely prominent way in this autocorrelation of the single photon data. And whatever you do, you can never get rid of this completely. There's one thing how you can circumvent this sort of in many practical cases. So if you add a physical delay to one of the cables, you can sort of shift this artifact out of your measurement range. So in practice, you can eliminate it as long as you don't need very long histogram ranges. So this is larger than, these signals at around 0, this crosstalk is larger than this periodic artifact, but you can remove it if you need to. So for really extreme precision measurements, you can get rid of it. And of course, you can do all sort of engineering to get this crosstalk as small as possible. Just very briefly, where could this crosstalk come from? So this is just a picture of a Timetag Ultra inside. So it could really be just analog crosstalk from one input to the other. Probably this is not what's really happening. Then you see that the signal that comes into the hardware enters a comparator chip on each channel. And if those chips are running on a common power supply, if one toggles, it will drain power, and that may change the operating conditions of the other. So that can also result in some sort of crosstalk. Then again, on the LVDS lines between the comparator and the FPGA, there could be crosstalk. And finally, of course, inside the FPGA itself, there could be crosstalk, which is something that is hard to, something that you have to live with. And indeed, to get this right, whenever we release a new bit file, we really test the crosstalk of between all sort of channels by letting the FPGA run with random input signals for almost a week. So that sort of makes the continuous integration quite heavy. So before any real bit file release, really heavily test the crosstalk for about a week, because if the routing inside the FPGA changes and routes really cross, you can get quite some heavy crosstalk. So that's really part of the homework that you have to do. Okay, so that's analog crosstalk. Now there's this funny periodic artifact, which is these periodic artifacts that are not very high, but they are present. And the nasty thing is that they continue very far out, so they sort of never die out. And these are relevant if you use time taggers for quantum random number generation of single photon events. So where do these come from? So imagine you have your tap delay lines, and try to sketch them here. So these are supposed to be bins, so they could be of a different length. Nothing is perfect. Every delay element can have an individual length. So imagine you have two tap delay lines and you've calibrated your bins perfectly. Okay, so you would guess that, okay, with these ideally perfectly calibrated bin sizes, everything should be fine. But now imagine you have on each of the channels, you have two quite big bins. You know their width exactly. You can't do much about it. They are in the FPGA like this, but they somehow are relatively large. In this case, the probability to observe a specific time difference will be different for the different delay. So the yellow arrows are supposed to be, a time difference of 0. So the event happens on the one channel and on the other channel at the same time. And the red arrows, these tilted arrows, they represent not a 0 time difference, but a specific time difference. And now you have to ask yourself, what is the probability of this event to occur? And for that, you have to integrate or sum over all possible occurrences, and this inclined one will hit these two large bins. So it will have a biased probability, a higher probability to occur. And this, even if you have perfectly calibrated your bins, leads to a bias of specific time differences being more probable to observe than others. Okay, and this is another thing, this periodic artifact is, if you want to do very, very high quality correlation measurements, is another thing that you have to deal with. And that took us some time to find ways to get rid of this. And in the time taker 20, we have reduced this one to 10 to the minus 5 or so, and the time taker ultra to 10 to the minus 7 or so. And indeed, this turned out to be relevant in this paper that is mentioned there, where a team in France measured the special interferometry of stars, so really non-classical light measurement of bright stars. All right. Okay, so once you've done all these stuff and dealt with all these tricky details, you can indeed push the time resolution to quite extreme numbers, and you see that here. So there's a time taker 20, which is based on quite an old FPGA, so it's exciting Spartan 3E, and even that one, even with that FPGA, you can achieve 28 picosecond RMS jitter. The time taker ultra is the Kintex 7 FPGA, and there we achieve 8 picosecond timing jitter. And with the time taker X, with the latest generation Kintex Ultra Scale Plus, indeed the timing resolution goes down to 2 picosecond RMS, as you see here. And by the way, I should maybe mention, to measure these data, simply what we've done is take a square wave, put it into a power splitter, hook that up to 2 inputs of the time taker, and measure multiple start, multiple stop correlation. And that's the data that these are the curves that are plotted there, and on the bottom, these are really all sort of pairs of channels against each other. All right. Okay, so that's what's inside these FPGA-based time to digital converters. So that's the TDC itself, the hardware side. In the next few slides, I would like to present you a little bit the architecture of the entire system. And that's shown here. So that's sort of the system architecture. So we start really with some type of single-ended signal, which could be a detector pulse that may look like this, so with a steep rising edge and an exponential falling edge, or it could be any other type of single-ended digital signal. And that goes into a high-speed comparator chip, where the reference level, the trigger level, is then provided by a DAC. And after the comparator, we then have a clean LVDS signal that represents the rising and the falling edge. So then this is sort of the crossing from a potentially analog world, potentially analog single-ended word, to the digital word in the form of an LVDS signal. So that enters into the tap delay line, and out of that comes this 11111000. So this raw tap delay output that goes into a thermometer decoder that evaluates sort of the bin number out of this chain at every clock signal. And okay, so the FPGA is driven by a 500 megahertz clock in case of the time taker ultra. Actually, for the time taker X, it's also a 750 megahertz clock speed. Okay, so then we have the delay number at which bin sort of the delay occurred. And then there's really a block which converts the delay number into picosecond, and that contains this continuous calibration of the tap delay line to really be sure that we always have this precise number of what is the actual length of these delay elements. All right, then at the same time, we simply calculate this, simply count the edges of the 500 megahertz clock to get a coarse time value, so that we have the number of clock edges passed since time 0 of this 500 megahertz clock. That's just a clock counter. And then taken together, we have the coarse time value and the fine time value, which is the delay relative to the last clock edge. And that taken together then gives a 16-bit time value in picoseconds. And this goes into an endpoint inside the FPGA, which then makes sure that all these time events are streamed in a stream fashion to the PC. And also into this data stream, we inject an overflow marker every time this clock counter rolls over. So this is really a rollover marker. Okay, then the FPGA is connected to an FX3 USB chip, and that goes to the computer, so that on the software side, there is an FPGA front end, basically, that on the one hand handles the hardware control, such as setting the duck value and other parameters in the FPGA, and it receives this stream of timestamps with the injected overflows. And the first thing that the backend does is that it converts these 16-bit time values, or the stream of 16-bit values, into 64-bit time values, integers, throwing out the rollovers. So after that, we really have a continuous data stream of timestamps that are 64-bit integers and just represent the time since the start of the instrument in picoseconds, which then for the later engine makes it quite nice to process stuff, because it's really just this monotonously increasing time value, somehow like the art. And this one with 64-bit in picosecond, it rolls over after 0.3 years or so. So as long as you don't measure longer than 0.3 years, you just there's just no rollover. Okay, and then in fact, what is on the left hand side in the FPGA, that is just represents sort of one single channel, but we have multiple channels. So the time text stream in reality, in practice, is a stream of the time value combined with the channel where the event actually occurs. And to make this whole thing information complete, you need the rising edges and the falling edges. And we found it practical that we actually separate the rising edges and the falling edges into different channels and sort of treat them like independent channels. So physical channel 1, rising edges will be channel number 1, and physical channel 1, falling edges will simply be channel number -1. So in this way, there's one easy and consistent way to represent the timestamps of rising and falling edges in one simple way. All right, and then this timestamp data stream goes into a processing engine that essentially takes care that all the measurement or analysis threads that are currently running see the entire time text stream. That's sort of it. That's the basis of the architecture. And now one thing that you can really do quite easily, or one of the first things that we've done, is to actually implement a logic analyzer. So that's now a 16-channel logic analyzer instrument. And the logic analyzer part is sort of software defined, right? And in terms of hardware specs, so we really have 2 picosecond resolution for every rising and falling edge, right? So a very, very fine, so it's a funny logic analyzer because it has this extreme precision for every edge. However, it doesn't have this huge sampling rate, so it has less than a gigahertz sampling rate. So let's say, or toggle rate. So the toggle rate is defined by the dead time of the TDC. So with the Time-Take Ultra, it would be about 500 megahertz. So you can detect any type of digital signals that are no higher than 500 megahertz and then really capture every toggle event. In terms of, and there's also an analog bandwidth that is given by the comparator. Okay, and so if you compare that to an oscilloscope, what is really special about this thing is that it offers this continuous streaming. So there's really no dead time after the trigger that records that thing, right? So on a scope of course, some scopes, I'm aware, as far as I know, they offer quite fast retriggering and then sort of allow you also to get multiple traces over to the computer relatively quickly. Nevertheless, it's certainly much more tedious in terms of processing, because here simply all timestamp on all events are continuously streamed to the computer, which means that you sort of get an infinite trace recorded to your PC. And it also allows you to implement very fancy software-defined logic triggers. So you could, I don't know, define triggers that, let's say you trigger on a specific condition where a setup violation or so has occurred, and the edge, the falling edge or rising edge on one bit is, I don't know, 20 picosecond off from where it should be, and only then you record the data, stuff like that. And also, again, it's very easy to implement software-defined protocol analyzer based on that. All right, so that's just one example of stuff that you can do with the architecture. Okay, and so in the next part, in the next couple of slides, I would talk about the time and frequency measurements and what we've done in that direction. So here is the setup shown. First is, let's say you have a 10 megahertz quartz that you would like to measure phase, frequency, and the drift, and a 10 megahertz atomic clock that you would use as a reference. And so both are applied to the time tagger, and then on the time tagger is running on its internal clock, which is, in this case, the silicon MEMS oscillator. And then, so the first thing that we would like to do is to average the atomic clock in a way, to sort of extract the period or the timestamps of the atomic clock and its period over a longer time. So this is briefly how it works. So in a way, on the software level, we would like to calculate an estimator of the period T of the atomic clock, and continuously update that one. So we somehow would like to measure in a continuous fashion the period of the atomic clock in the time basis of the internal silicon MEMS oscillator. And the straight or an easy way you could think about how this could be done is to really just do a running average calculation over a number of, let's say, the past 1,000 edges or so. If you think about that in a bit more detail, you realize that actually using a PID controller to do that on the software-defined way is sort of the natural approach, because in this case, you tuning the parameters nicely, you have in the PID from the integral part, you already have the damping and the limitation to a finite range of clock edges, and it's sort of the most or one of the most complete ways. You could certainly use other controllers as well, but at the end of the day, it's in fact what you're doing here is locking an estimator for this period T to the actual signal. All right, so in a way, at every clock edge of the atomic clock that you receive, you have this predictor when you expect the next time tag of that clock. And then the deviation of the expected time tag and the actual measured time tag, that's your error value that you feed back into the PID controller. All right, and in this way, you get this, you sort of recover this clock period T from the data stream relative to the internal clock oscillator. Okay, so now we have essentially averaged the clock and received a very precise value for the atomic clock period. The next thing that we do is that we actually swap the time reference frame. So the next thing is that we say, okay, we assume, we now say that this atomic clock has the period, let's say 10 megahertz, it has a period of 100 nanoseconds. And at every time we say, okay, this was 100 nanoseconds, so then it remains that we recalculate the timestamps of the other channel relative to this this atomic clock channel, where we have now sort of swapped this estimator, or changed from this estimated value, which is probably very close to the expected 100 nanosecond, to the nominal value of that atomic clock, or whatever other reference. Okay, and in this way, we have sort of in a software-defined way swapped time reference frame from the silicon MEMS oscillator to whatever external clock that is applied. And maybe to go beyond that, so in this particular example, I've just talked about a periodic clock signal. This could also be clock recovery from data where you have missing edges or stuff like that. So in fact, because it's completely software defined, it's very easy to implement very complex clock recovery from whatever funny signal, and then measure frequency stability relative to that signal or of that signal. Okay, so once we have okay, so maybe one thing that's important to mention. So why do we do it this way? Why don't we just take the atomic clock and run the time tagger itself on this atomic clock? And the reason is that all this fancy calibration of the TDC requires somehow signals that are independent, or requires that the input signal is independent of the internal clock. So in fact, to really, so the only way to maintain this extremely high calibration is to have sort of uncorrelated signals. And that's why it's so powerful to apply the clock signal to an input and then do the clock reference frame change on a software-defined level. All right, and once you have done that, you can simply use the standard, let's say in this case, so this formula is taken right from the stable 32 libraries. So you can use the typical metrics and calculate phase, frequency stability, ADEF, MDEF, TDEF, etc. And we first thought that we might just use the stable 32 libraries, but then Markus actually went ahead and implemented or rewrote part of those algorithms and converted them directly into time-tag processing threads to increase the performance and make it possible to run all these metrics right away on the fly. Okay, and this, at the end of the day, this is what the whole thing then enables. So you apply your reference clock to one input of the time taggers and all your other clock signals. The device is under test to other inputs, and enable the software clock feature, and then you can compare up to 18 clocks in parallel, and measure phase frequency and all these standard metrics. And the frequency range of the clocks is essentially from DC to 750 megahertz, which is a very large range. And at the end of the day, the noise floor for LN deviation measurements is somewhere in the 10 to the minus 13 range, which means is equivalent to a phase noise essentially of the average signal that is somewhere in the 100 femtosecond range. Okay. All right, and this is now what Ahmad, what you mentioned at the beginning. One thing that we did at the ITSF. So another application. Sorry, there's a phone ringing here, and I actually don't know how to turn it off. So I hope it will go off automatically in a minute. So another application is not just to measure 10 megahertz clock signals, but to measure 1 PPS signals. And the setup here was were 2 NUCs, and well, I maybe should even pass the word on to Ahmad, who has set this all up. So these are 2 NUCs where we look at the 1 PPS signals from the NIC and the 1 PPS signals generated from the CPU in user land using the software-defined pin. And in this way, we really have 1 PPS signals coming out of the unit at 2 different places, and then the 2 NUCs are linked via PTP. So the 2 NICs are synchronized via PTP, and then the NIC and the CPU are on each NUC are synchronized using PTM. And in this case, there are 4 different 1 PPS signals, and we hook them up to the time tagger. And the signals that you basically then see are sketched below. So at every second, there is a 1 PPS signal coming out, and they're all slightly differing. So we measure the timestamps on all 4 at each second. And what you see on the top right, so that's a screenshot of the measurement that we did back then. What you see on the top right are really the histograms after letting this thing run for some time, the histogram of the time delays. And the left one is the PTP, so that's the NIC versus the NIC. And you see there that the width of the histogram is in the range of, I don't know, 10 nanoseconds or so. And on the right-hand side, you see the CPU versus the CPU. So this is sort of the whole synchronization chain. And you see that this also looks like pretty Gaussian with a width of around about 50 nanoseconds. However, you also see that there are some rare events, especially on the right-hand side. So the thing is a little bit asymmetric. And there are some rare events that extend to almost 100 nanosecond. And I guess this is something that at least me, I haven't understood yet, where those events might be coming from. So okay, so it proved quite useful to be able to record all those timestamps in continuous fashion, and hook them up there and then plot them right away. And one thing that would be very nice to do in the next measurement is to simply record all time differences values on a time trace, and that's something that we'll be doing shortly, I guess. All right. I'm looking at the clock, and it's round about 1 hour that I've talked. So
there is an extended version of what we did last time, and I wanted to share with you. Maybe it's interesting. So basically, this time we got this like NUC 11 TNH, which has basically 2 PPS, two NICs, and we were trying to test like the effect of using a like a TCXO instead of an XO on PTM, and we're gonna extend it like basically without PTM, and then on basically PTP, and then we want to also test because we want to see the value proposition of if like you add a TCXO to the CPU or to the NIC, is that really gonna make anything different or not? So what we did is we added like the 4 permutations, like because you have the CPU and you have the NIC. So you want to have a CPU either TCXO or XO, NIC TCXO or XO. So these platforms, they come with a NIC that is built in and a NIC that is sitting on a M.2 key B. So I modified one of the CPUs to use a TCXO from SciTime, and that was like a 38.4 megahertz. And then I modified both of the NICs, the second NIC basically, for all the machines to be a 25 megahertz. So then you have 4 permutations. You have basically CPU with XO, NIC with XO, CPU TCXO, NIC with XO, CPU with TCXO, NIC with XO, and then you have like CPU with TCXO and NIC with TCXO, all 4 permutations. And then I ran the experiment, and it was very easy to use like the time trigger, because you don't have necessarily one reference. You can put any one of them to anyone. That's the beauty of the correlation. And one thing I was wondering, like, if it's possible, it would have been great to have somehow an option to overlap all of these things together. I didn't find that. Like, I had to have them all sitting separate. So then I had that issue with sometimes, because the CPU just uses a toggle. So I had basically the 180 thing. So I was simply just changing this, flip it like up or down, like, and it would have solved the whole problem. So then it's very interesting. You can see some minor effects, but overall it doesn't make that much difference when the frequency is low. When the refresh time is high, because there's not that much holdover to really see a significant difference between TCXO or an XO. But as you put the refresh time much less, let's say for example every 5 hertz, like 0.2 hertz every 5 seconds, then you start really seeing things, and you see it like basically in some end of this tail basically started to increase. It's very interesting. So, back to you.
Very cool. Yeah, thank you very much, Ahmad. Very, very cool. So this tail, any idea where this could come from? What that could be?
So as far as I understood is like you're hitting basically a like there is a point where you're getting the quanta, and that this comes from the quanta that you have in the quantization from the timestamps. Sorry, this guy is pretty wild. So on the quantization that you have on the timestamping over the packets that they go through the PCIe. And
Okay.
that's all I understood. Again, I definitely don't know much. I'm just like, and this is like a telephone game. This is what was explained to me. I'm trying to explain it. So as it goes further, the entropy increases. Packet delay
Yeah,
variation. You know?
yeah, yeah, very cool. It
But we'll
might be
find out
interesting.
more.
Yes, so on using the Python libraries, it should be possible to, and Mirko has done that in other cases, so that you really simply plot the time difference, the delay for each point. So you get it, instead of just the histogram, you get also the whole trace, because 1 point per second is totally fine to run that for, I don't know, a couple of hours and just record all the data points. And then we might see that at some point, um, when you have these outliers, maybe multiple outliers come in a correlated fashion, or maybe not. But this would probably give a lot more insight. So let me ask Mirko to. So if you could store the data from measurement, do the file dump, send it over to us, and we will give it to Mirko, and he can play with it and start processing it in many different ways. And once he has done it, he can shoot it back at you, and you can then use the same ways to
Yeah.
record that also live.
Yeah. Also,
Very cool.
one other thing. Again, these are more again technical related things. Perhaps we can have them in another meeting. Is like it would be good if there is also the possibility to add a constant delay when you have some like signal that is already like offsetted by a constant, and then you can expand that window there. Because right now, let's say for example, when you turn off PTM, this is something like you can see it even in Kevin's presentations. When you turn off PTM, you have the constant like and keep TGPIO, you will have a constant offset, which is basically how things are working. It doesn't get compensated. But then things
Okay.
start getting like that Gaussian curve around, let's say, I don't know, 400 nano. And then if you want to use like, let's say the current method, I have to keep the whole window open while I want to observe what's going on there. While it would have been good
Understand.
if I
Yes.
was able to add a, yeah, it's very interesting. Like
Yep,
using,
absolutely. So in fact, this is there. So if you go to the
oh, I see.
settings, you can add any delay. So up to a second or so. Yeah, it will then just buffer the time text stream. So it's also done on the software level. You will simply take the time text stream and add the value to it and buffer it and make sure that it's again that the sorting in the time text stream is correct, so it will resort them in the right way, and in that way it should work out. Try if it should be visible under the settings wheel.
Should we go to question period? Are we done with the presentation, or there's more?
I have a lot more. I have more. I have more topics. No. I have more topics on photon number resolution and so on, but I would skip them. So I suggest to.
No, I don't mind. I don't mind. Let's add any knowledge, because it's going to stay there and it's going to be recorded. But if anyone wants to ask a question now and they have to leave, if not, we'll proceed with the presentation. Hearing none, I think everyone's fine. Let's continue with that. No compromises. Okay. I'm sorry, like I know it's very late in Europe, but trust me, it's gonna be recorded, so you will get less questions.
So let me get this back. Hang on for a second here. Okay, so that's now. So these are sort of random topics, and I'll try to run over them quite quickly. So three topics that I would like to share with you, and one is photon number resolution. So it's a completely out of time and frequency, but I hope it's interesting, as some of the, let's say, histogramming methods are quite powerful and useful. So short introduction about superconducting nanowire single photon detectors. So this is a very new type of single photon detector that is based on a superconducting wire, nanometer thin superconducting wire, and you apply a bias current through that wire, and if that wire absorbs a single photon, superconductivity will break. It will become normal resistant, and that is a huge, so from superconductivity to some finite resistance, that's like a huge spike, and you detect that one as a little jump. Okay, and these measurements were done together with CN Quantum, who's probably the leading supplier of single photon detector, superconducting single photon detectors from Delft in the Netherlands. Okay, so what you do is you take a pulsed laser, a femtosecond laser with a 50 megahertz wrap rate, and you shoot at the single photon detector. And you take the timestamps from the laser trigger and the timestamps from the single photon. And okay, here do the whole measurement. You see that the whole jitter is about 10 picoseconds. So the main jitter comes from the single photon detector and not from the electronics, which is good, or good for us, let's say. Okay, and then what we look at here, so now you crank up the laser so that maybe one or maybe two or three photons can be in one laser shot. This will lead to a shift of the leading edge of the detector. And you see that on the left-hand side. So if you do a histogram of the delay between the laser and the photon detection event, most of the events have one single photon, and they here have a delay of about 150 picoseconds. But some events have two photons, and they come a little earlier, so the delay here is only about 120 picoseconds. That's the second spike, and there's a little bump just below, a little less than 100 picoseconds, which are three photon events. And you may see a fourth one if you are very kind. But obviously, this is not very well distinguished. So you somehow see the events, and you see, okay, they are probably there, but you couldn't really separate these events very nicely. And if you look at the falling edges and you look at the histogram there, it's just one big blurred thing. Also, there's really not the full information there, and you can't distinguish them. But what you can do is you can do a multi-dimensional histogram. And that's what's plotted here. So on the x-axis, that's the delay between the rising edge and the laser, and the y-axis is the delay between the falling edge and the laser pulse. And suddenly you see much more stuff coming up. And if you now, so you can now imagine if you tilt that whole thing, so it's a little bit tilted. That's why if you just project it to one axis, it's all blurred. But if you tilt the whole thing, you can actually start to distinguish these pulses much more precisely. Okay, and then there is one more thing. You could, let me go back once. You see this zigzag structure in the data, and you would like to get rid of that, or the question is, what is that? And it turns out that this comes from, so these pulses, they have this long tail, and if they overlap, that results in a shift of the trigger event, so that the data is much cleaner if you don't have two precisely subsequent events in this pulse train. And so also that you can do, so because you have this time-to stream processing engine that allows you to know about the previous events, and you can implement filtering on the software level that allows you to throw out one of the edges. And in this way, as you see on the left plot, you get a very clean plot that allows you to do this photon number resolution. So actually, it turned out quite powerful by combining these rising and falling edges. You can indeed do photon number resolution on these superconducting detectors. All right, I'll be short on this one. Now, just a very brief one of one quite interesting application of the two things, superconducting detectors and time taggers. So one thing that we're working on is a technology to be able to measure optical signals at a bandwidth of around about 500 gigahertz or more. And I mean, so this could be very fast electro-optic modulators. This could be signals that occur in femtosecond laser cutting or laser welding. Any type of really fast optical signals that you might be interested to measure. And I mean, how do you usually measure fast optical signals? So you take a fast photodiode and a very fast oscilloscope, so maybe the latest and greatest Keysight scopes, which bring you up to 110 gigahertz or so. And okay, so what we would like to do instead, bring the bandwidth up to 500 gigahertz, at the same time provide about 7 decades of dynamic range, and also being able to measure these signals at femtowatt sensitivity. And the technology or the principle that you use here is quite a simple one that's actually known since quite a while from these fluorescence lifetime measurements, which is when you shoot a pulse laser at a sample and you look at when the emitted photon came out. And the only difference is, and you do that by doing a repeated measurement. That's why it's a sampling scope and not a real-time scope. So you need to do a repeated measurement. You shoot at the sample and you measure this histogram of time differences between the trigger and the detected photon. Okay, and in this case, so this is sort of a proof of concept that we've done some time ago at the ECO conference, where we have used this just SFP plus optical fiber communication module with I think it was a 10 gigahertz 10 gigabit fibercom module in the infrared. Oh no, it was a not infrared, it was in the visible 690 nanometer, so if I remember correctly. Okay, so what you do is you take your SFP plus module and you put some bit pattern on that. And you take the optical signal and you attenuate it by around about 100 dB. So you sort of bring it down from somewhere in the milliwatt optical power range to a femtowatt optical power or below, such that only a few photons are left, and you can start detecting these signals with a single photon detector. So from milliwatt, you bring the signal average power from milliwatt down to something like 1 million photon counts per second. Okay, and then you repeat. So you shoot out this bit pattern in a repeated fashion. And that is what you see there, this sort of dark line that I called 100 dB attenuated signal. And this thing is so much attenuated that you will only see a single photon every now and then. So out of this original signal, only a few random photon events are left. However, the probability to actually detect a photon is proportional to the original intensity. So where there was intensity before, you have a high probability to detect a photon, and where there was no intensity, you will very, very likely not get a photon. Okay, and then what you do is you measure a start-stop. You perform a start-stop measurement between the trigger of the signal generation and the actual photon detected. And after putting those into a histogram, you get back your original signal as a photon counting histogram. Okay, so now you have done a very complicated thing to just get the same thing that you could measure with an oscilloscope. But the twist is that the whole thing is limited only by the, and okay, so here we have shown that it actually works, and you can do eye diagram measurements and so on. But the twist is that the whole method, or the bandwidth of that method, effectively is limited only by jitter. So, and that is the jitter of the single photon detector and the jitter of the electronics in a combined fashion. So, and that means the time between the photon being absorbed on the detector and the actual output pulse that is generated, or the time tag that is captured from the output pulse, that one is not always perfectly deterministic and perfectly the same. This could be a little bit earlier and a little bit later. So this is just jittering due to imperfections. Okay, and so if you do the math, then if you would have a detector with 1 picosecond full width half maximum jitter, that would correspond to a bandwidth of about 440 gigahertz. Okay, and the electronic signals involved in the whole thing. So the analog bandwidth of the signals that come out of the detector is not that extreme. So it's maybe the rise time of the detector pulse is 100 picosecond or so. Maybe you increase that a bit further. So it's like on the order of 10 gigahertz or so. Is the analog bandwidth that's in the signal. So you don't need to do extreme analog electronics, but still, because the effective optical bandwidth is given only by jitter, you effectively measure signals at these extremely high optical bandwidth. Okay, now, of course, producing a TDC and a photon detector with just 1 picosecond for width of maximum jitter is not easy, and it has not been done before. But so that's sort of the homework. So the homework is to develop a single shot TDC with 1 picosecond or lower jitter, and also to detect the single photon detector with such a low jitter. And with the conventional or classical spot detectors that have been around, there the jitter today is at about 20 picosecond or so, and it's not obvious that we could bring those down further, but with the superconducting detectors, it's really within reach. And the guys that we're working together with is the team of Wolfram Pernies. He was at Uni Münster and is now, since a year, I think he's at the University of Heidelberg, just next to Stuttgart. And he's making these very low jitter superconducting single photon detectors based on this waveguide silicon nitride, I think, waveguide, and this niobium nitride nanowire that he deposits on that one. And because he uses this waveguide, he can bring the kinetic inductance of the superconducting wire down, and that really dramatically improves the jitter. All right. Another way is to really fabricate a very, very short nanowire and just put it across a waveguide. And in fact, so in this way, you get a single photon detector that has a low detection efficiency, but a very low jitter. So it sort of allows you to trade in detection efficiency and win jitter, which is totally fine for this particular application because we typically attenuate the signals anyway. Okay, and in this way, so with the TDCs that we have in FPGA so far, which are 2 picosecond, we would already be at an effective bandwidth of 200 gigahertz or so. And to really push this further, our homework is to really implement a sub-picosecond time-to-digital converter. And we set out to do this in a 22 nanometer FTSOI process. And I have 2 PhD students working on that. So the idea is really to build an ASIC TDC, and it should be single shot capable. So this delta sigma and SAR architectures are ruled out because they need repeated measurements. The dynamic range should be larger than the clock period. That's important. And the goal is really to go to 1 picosecond or below. Okay, and we have first started out looking at the different processes that are around, and CMOS is one obvious player. Of course, the FinFET, the Intel's 22 nanometer process, for example, or even lower, could be interesting. However, FinFETs don't have backgate biasing and limited control of the device, so only multiple fins. And of course, it's also a very complex and costly process. And in fact, fully depleted silicon on insulator delivers a performance similar to a FinFET, but in addition, it enables backgate tuning. And that is for us, we believe will be the key to implement delay elements of these tap delay line TDC that have a very, very high propagation speed by really tuning the backgate into ranges that are usually not used. And in this way, according to our estimation, 22 nanometer FTX should really be the fastest analog process that is around today, and that's why we choose this one. And that's the basic idea of the ASIC TDC. And yeah, so Ahmad, I'm very happy that you mentioned Stefan Hensler before. So these are two pictures taken out of his book that is shown here, that was published with Springer in 2010. It's the tap delay line TDC as the coarse time measurement, and then a fine time measurement based on a Vernier TDC, and that is similar to the tap delay line TDC, but has also delay elements in the clock line, right? And that sort of enables a differential measurement and further enhances the resolution. All right, and that's roughly the architecture. So it's really a tap delay line and thermometer decoder for the coarse one with a range of 1 nanosecond, so delay range 1 nanosecond, which means that it's the chip will be driven by 1 gigahertz clock. And the delay element size there is around 20 picosecond. And then the fine one will be, so a delay of about 1 picosecond and a range of 40, so just 40 elements. All right, and we have done quite some analysis of the noise, and according to our estimations, really the deterministic jitter from the power supply temperature, bulk supply, and so on are all well below 100 femtoseconds, so this is all fine. And at the end of the day, really the RMS jitter, the entire buffer chain will be quite an important factor, and this is one of the key things that we are optimizing in the process. All right, so that just very briefly. So tape out is will happen sometime in the next year, and we'll see what happens and how far we can push the limits there. on the TTC ASIC design. All right, so this is now the last slide. So I hope I've convinced you that really a multi-channel time-to-digital converter combined with a hopefully well-written time-tag stream processing engine really provides a very powerful tool for digital measurements, and I hope that it may be useful for particularly for the community where you guys are all working in, which is time and frequency measurements and synchronization across computer devices and architectures. And yeah, with that, I would like to thank you very much for your attention, and happy to answer any questions. And if you have any questions after the talk, also feel free to shoot me an email or just call me on my office phone at any time. Really happy to talk about all technical details. Thank you very much.
Wonderful. Thank you so much. So I think George has a question. George, can you unmute and ask your question?
Yeah, thank you for the talk. Yeah, just a simple question. I'm curious, is going to the ASIC, is this also more cost effective in the end?
That's a good question, Georg. Yeah, thank you very much. I probably with the numbers and the quantities, sales quantities that we have today, it's probably not. So, yeah, I guess so. We're really not yet a large company, and we're not selling huge quantities. So I think at the moment it will not be initially it will not be really much more cost effective. But of course, at a later stage it may be. And to be honest, I also really do not know yet for what this TDC chip might be used for. Besides these really high-end measurement applications, there's probably one thing that is quite relevant, and that's power consumption. So these FPGAs, they have a huge power consumption, and as a lab measurement tool, that's fine, I guess. I mean, you don't worry so much about whether this thing consumes 10 watt or 100 watt. But if you have a TDC chip that is very accurate, and that's part of some embedded measurement system, or a LiDAR sensor in a car or whatnot, that thing, it may be very important that the power consumption is low. So there might be a completely different market for TDC chips with high precision and low power consumption in embedded measurement systems that I do not yet see, or I'm not aware about yet. And I somehow have the feeling that this may be, at the end of the day, one of the wider application. Does that answer your question?
Yeah, of course. Thank you very much. Yeah, I see it's like often yeah, economics of scale, kind of.
Yes.
Yeah. Okay. Yeah. Great stuff. Yeah.
One thing I wanted to clarify is that like you're aiming to have actually a chip, like similar to, let's say, for example, TI or like some other vendors have, like a TDC chip?
Yes.
And would you also use it for just internal consumption, or you will sell that as a product as well?
I'm really happy to sell it as a product, for sure.
That would be great. Yeah. So would that be also a bi-directional, like you know what I mean? Like basically, it will the start stop can exchange, right? You can get the stop before start, like they call it bipolar EDCs. Would that be a
Yes.
bipolar?
I guess yes. So what we will be doing, I think, is it will be a multi-channel one in a way. And so if you run it, if you run it on a base clock, on whatever, let's say, gigahertz clock, and you have two independent inputs that are the start and the stop, you could interchange them, so they're completely interchangeable. Yes.
Would they work automatically, or you have to interchange it? You know what I mean? Like for example, how you have it in your time trigger, it's really amazing. Like it doesn't matter who comes first, you always have it. So
Yes,
I mean,
it would be
in
like
reality, I had a hard time building this with two discrete TDCs. I think was a TI TDC 7000 or something. I literally had to use two of them, and then basically use some logic in the back.
Yes, this will be, so it will be like in the time taker. So this will be equivalent and interchangeable, sort of by
I definitely
software.
see a need for that. There is no such advanced TDC right now in the market, because we're literally exploring how we can add some, like, basically next level of improvement in the time card. And we looked at TDCs and we saw like we have to dump like so many discrete TDCs to get what we're looking for, and then we gave up. And then again, we looked at like what is really necessary in terms of like requirements, and that was really not there. But slowly, as time card is becoming more like more applications are emerging, so we're looking that. And I was also wondering, and I don't want to put you on the spot, but we were wondering if we can get, let's say, Swabian to do like some work also on the time card for the like the comparison, because there is another work stream Julian is working on with Anand from Calnex on basically having the time card do act as a measurement tool as well, and it would be great if we have like some of these limited functionalities, let's say, because it's an Atrix 7, is not like a what you guys have. I think you guys have some ultra scale or something. I didn't pay attention. So you have
Yes.
of course, yeah. So
yeah, absolutely.
one more question from my end is like, if you had, do you have like any message you want to give to these? Because we have here, I think, representative from some ASIC companies here. I mean, I think we have someone from Microchip or from TI or something. Like, is there something they can help with, or like, is there
Good
any
point.
word of encouragement?
It's a good point. Yeah, so for sure we're looking for ASIC developers. So I mean, I have two PhD students, and they're really doing a great job. And at some point we'll have to make that soon. We'll have to make the transition from student level project to a commercial ASIC project, and for that so we'll probably have some interesting positions for people that want to build up an ASIC team.
Wonderful. Any more questions from the audience? And I think you broke the record in terms of length of a presentation. I think we had an hour and a half. Right now we're hour and 40 minutes, so hitting 100 minutes. Hearing none, I think that should be it. And again, would you please just put on your on the screen your email, just in case if anyone at this point in the recorded version looks at like and they want to message you. I hope you had it already in the presentation, right?
I think I didn't have it, but I can put it here.
Yeah, just email, so then everyone will know how to contact you. Oh, perfect. It's very simple. So it's your name at swabianinstruments.com. Perfect. Thank you very much. Thank you, everyone.
Thank you very much, everyone.
See you in 2 weeks with a presentation. I think it's the next on the calendar is it's George from Deutsche Börse. Perfect.
Yeah, that's
Awesome.
right. Yeah.
Awesome. See you guys in
Very
2
much
weeks.
forward to it. See you
Thank you.
guys.
Have a nice day.
Bye-bye. Bye, everyone.